Grounding a generator in a separately derived system requires a specific approach to ensure safety and proper operation. When a generator operates as a separately derived system, meaning it supplies power independently of the utility source, it needs its own grounding system. The key connection is from the generator to the grounding bus, which is often located in the main overcurrent protection device or a separate enclosure. The grounding bus serves as the central point for connecting all grounding conductors, providing a low impedance path for fault currents to return to the source. The correct way to ground such a system involves several steps. Firstly, identify the separately derived system. This means confirming that the generator's output is electrically isolated from the utility power supply. This isolation is crucial because it prevents circulating currents and ensures that ground fault protection operates correctly. Secondly, establish a grounding electrode system for the generator. This typically involves driving one or more ground rods into the earth near the generator location. The number and type of ground rods depend on local electrical codes and soil conditions. The grounding electrode system provides a direct connection to the earth, helping to stabilize the voltage and provide a path for fault currents to dissipate safely. Thirdly, connect the generator's frame to the grounding electrode system using a grounding electrode conductor. This conductor should be sized according to the generator's output capacity and the requirements of the National Electrical Code, specifically NEC Table 250.66. The grounding electrode conductor ensures that the generator's metallic parts are at the same potential as the earth, reducing the risk of electric shock. Fourthly, establish a system bonding jumper at the generator. The system bonding jumper connects the generator's neutral conductor to the grounding bus. This connection is critical for creating a low impedance path for fault currents to return to the generator. The size of the system bonding jumper is determined by NEC Table 250.102 code and depends on the size of the generator's largest ungrounded conductor. Fifthly, ensure that all metallic enclosures, such as conduit and junction boxes, are properly grounded and bonded. This is achieved by using grounding conductors that are connected to the grounding bus. These grounding conductors should be sized according to NEC Table 250.122, which specifies the minimum size of equipment grounding conductors based on the rating of the overcurrent protection device. Sixthly, connect the grounding bus to the neutral of the service. This connection ensures that the generator's grounding system is effectively integrated with the overall electrical system. The neutral conductor should be connected to the grounding bus using a properly sized conductor, as determined by NEC 250.24b. It's important to verify that the size of the conductor matches the rating of the overcurrent protection device. When installing the grounding system, pay attention to the following considerations. Firstly, use the correct type of grounding conductors. Grounding conductors are typically made of copper or aluminum and must be properly sized and insulated. The type of insulation depends on the application and environmental conditions. Secondly, ensure that all connections are tight and secure. Loose connections can create high resistance, which can impede the flow of fault current and compromise the effectiveness of the grounding system. Use appropriate connectors and tools to make secure connections. Thirdly, protect the grounding conductors from physical damage. Grounding conductors should be routed in a way that minimizes the risk of damage from impact, abrasion, or corrosion. Use conduit or other protective measures when necessary. Fourthly, test the grounding system to verify its effectiveness. After installing the grounding system, it's essential to test it to ensure that it meets the required standards. This can be done using a ground resistance tester, which measures the resistance between the grounding electrode system and the earth. A low resistance reading indicates that the grounding system is functioning properly. The neutral of the service also plays a critical role in the grounding system. The neutral conductor provides a return path for unbalanced currents and helps to stabilize the voltage. It's important to ensure that the neutral conductor is properly sized and connected to the grounding bus. The size of the neutral conductor should be based on the calculated neutral load, as determined by NEC 220.61. The connection to the grounding bus should be made using a properly sized connector. In addition to the above steps, it's important to comply with all applicable electrical codes and standards. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems. Local electrical codes may also have additional requirements. Consult with a qualified electrician or electrical engineer to ensure that your grounding system meets all applicable requirements. Proper grounding is essential for protecting people and equipment from electrical hazards. A well-designed and properly installed grounding system can help to prevent electric shock, reduce the risk of fire, and improve the reliability of electrical equipment. By following the steps outlined above and complying with all applicable codes and standards, you can ensure that your generator is grounded safely and effectively. For example, consider a generator rated at 100 amps. According to NEC Table 250.66, the minimum size of the grounding electrode conductor for a 100 amp generator is number 8 copper. Similarly, according to NEC Table 250.102 current, the minimum size of the system bonding jumper for a 100 amp generator is also number 8 copper. These sizes are based on the assumption that the grounding electrode system consists of one or more ground rods. If the grounding electrode system consists of a concrete encased electrode or a ground ring, the minimum size of the grounding electrode conductor may be different. It is essential to consult the NEC and local electrical codes to determine the correct size of grounding conductors for your specific application. Another important aspect of generator grounding is the location of the grounding electrode system. The grounding electrode system should be located as close as practicable to the generator. This minimizes the length of the grounding electrode conductor and reduces the impedance of the grounding path. The grounding electrode system should also be located in an area that is free from physical damage and corrosion. Avoid locating the grounding electrode system in areas that are subject to flooding or excessive moisture. The type of soil in which the grounding electrode system is installed can also affect its performance. Sandy soil typically has a higher resistance than clay soil. If the soil resistance is high, it may be necessary to install additional ground rods or use a ground-enhancing compound to improve the effectiveness of the grounding system. It's also crucial to maintain the grounding system properly. Regularly inspect the grounding conductors and connections for signs of damage or corrosion. Tighten any loose connections and replace any damaged conductors. Test the grounding system periodically to verify its effectiveness. A well-maintained grounding system will provide reliable protection against electrical hazards for many years. In summary, grounding a generator in a separately derived system involves establishing a dedicated grounding electrode system, connecting the generator frame to the grounding electrode system, establishing a system bonding jumper, ensuring that all metallic enclosures are properly grounded, and connecting the grounding bus to the neutral of the service. Compliance with all applicable electrical codes and standards is essential. Proper grounding is critical for protecting people and equipment from electrical hazards. Consider the implications if a fault occurs on the generator side. Without proper grounding, the fault current may not have a low impedance path back to the source, which can result in elevated voltages on metallic parts and an increased risk of electric shock. A properly grounded system provides a low impedance path for fault current, allowing the overcurrent protection device to quickly clear the fault and minimize the risk of electrical hazards. Think of the grounding system as a safety net that is always there to protect you and your equipment. A reliable grounding system is an investment in safety and peace of mind. By following the guidelines outlined above and working with a qualified electrician, you can ensure that your generator is grounded safely and effectively. Remember to consult the latest edition of the National Electrical Code and local electrical codes for the most up-to-date requirements. Grounding requirements can vary depending on the specific application and location, so it's important to stay informed and comply with all applicable regulations. Understanding the principles of grounding is essential for anyone who works with electrical systems. Grounding is not just about connecting wires to the earth, it's about creating a safe and reliable electrical system that protects people and equipment from electrical hazards. By taking the time to learn about grounding and following best practices, you can help to prevent electrical accidents and ensure the safe operation of electrical equipment. The NEC provides specific guidance on the selection and installation of grounding electrodes. Common types of grounding electrodes include ground rods, ground plates, and concrete encased electrodes. The NEC specifies the minimum size and length of grounding electrodes, as well as the spacing requirements for multiple electrodes. It's important to follow these requirements to ensure that the grounding electrode system is effective. The grounding electrode conductor connects the grounding electrode to the grounding bus. The NEC specifies the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding electrode conductor should be installed in a manner that protects it from physical damage. The system bonding jumper connects the neutral conductor to the grounding bus at the source of the separately derived system. The NEC specifies the minimum size of the system bonding jumper based on the size of the service entrance conductors. The system bonding jumper should be installed in a manner that provides a lower impedance path for fault current. Equipment grounding conductors connect the metallic enclosures of electrical equipment to the grounding bus. The NEC specifies the minimum size of equipment grounding conductors based on the rating of the overcurrent protection device. Equipment grounding conductors should be installed in a manner that provides a low impedance path for fault current. In addition to the NEC requirements, local electrical codes may have additional requirements for grounding electrical systems. It's important to consult with a qualified electrician or electrical engineer to ensure that your grounding system meets all applicable requirements. Grounding is an essential aspect of electrical safety. A properly designed and installed grounding system can help to prevent electric shock, reduce the risk of fire, and improve the reliability of electrical equipment. By following the guidelines outlined above and complying with all applicable codes and standards, you can ensure that your electrical system is grounded safely and effectively. The purpose of grounding is to provide a low impedance path for fault current to return to the source. This allows the overcurrent protection device to quickly clear the fault and minimize the risk of electrical hazards. A properly grounded system also helps to stabilize the voltage and reduce electrical noise. Grounding is not the same as bonding. Grounding connects electrical equipment to the earth, while bonding connects metallic parts together to create a low impedance path for fault current. Both grounding and bonding are essential for electrical safety. The NEC provides detailed requirements for both grounding and bonding. Grounding and bonding are often used interchangeably, but they are two different concepts. Grounding connects electrical equipment to the earth, while bonding connects metallic parts together to create a low impedance path for fault current. Both grounding and bonding are essential for electrical safety. Grounding is the process of connecting electrical equipment to the earth. Bonding is the process of connecting metallic parts together to create a low impedance path for fault current. The grounding system should be designed to provide a lower impedance path for fault current to return to the source. The grounding system should be designed to minimize the risk of electric shock. The grounding system should be designed to reduce the risk of fire. The grounding system should be designed to improve the reliability of electrical equipment. The grounding system should be designed to comply with all applicable electrical codes and standards. The grounding system should be inspected and tested regularly. The grounding system should be maintained in good condition. The grounding system should be protected from physical damage. The grounding system should be protected from corrosion. The grounding system should be properly labeled. The grounding system should be properly documented. The grounding system should be understood by all personnel who work with electrical equipment. The grounding system is an essential part of any electrical system. A properly designed and installed grounding system can help to prevent electric shock, reduce the risk of fire, and improve the reliability of electrical equipment. Remember to consult with a qualified electrician or electrical engineer to ensure that your grounding system meets all applicable requirements. Firstly, ensure that the generator frame is properly grounded to the earth. Secondly, bond the neutral conductor of the generator to the generator frame. Thirdly, use a grounding electrode conductor to connect the generator frame to a grounding electrode, such as a ground rod.